Okay, now let us go and solve some problems. On DFT. Very well, let us look at the first example. It says that compute the 4-point DFT of the sequence x of n, which equals to 0, 1, 2, 3, the position 0 being the origin, and to sketch the magnitude and phase spectrum. Very well then, let us go to the solution. So we know from the equation of direct transform, x of k equals the running sum where small n goes from 0 to capital N minus 1, x of n e to the power minus j 2 pi nk over n. Now from the given expression, the given signal, we can easily determine the length. So the length of the signal x of n, where n is equal to 4. So the direct transform equation can be simplified to x of k n, where n goes from 0 to n minus 1, where n is 4, so n minus 1 becomes 3, x of n e to the power minus j twice pi nk over 4. So what we are to do now is decompose this summation and write it as individual sum. So for n equal to 0, this becomes x of 0, and e to the power minus j 2 pi nk will become 0, and e to the power 0 will become 1. So this remains as 0. Then again, when n equals 1, x of n becomes x of 1, e to the power minus j 2 pi nk over 4, this becomes e to the power minus j pi k over 2, because n is equal to 1 and we have cancelled this 2 with 4, and so it becomes minus j pi k over 2. Then again, for the next term, it becomes x of 2 e to the power minus j k pi, where n is 2, 2 times 2 is 4, and 4 gets cancelled out, and all we are left with is minus j pi k. And the final term, x of 3, which is equal to x of n becomes x of 3 and e to the power minus j 3 pi k over 2. So now from the given sequence, we plug in the value of x of 0, x of 1, 2, and consequently 3. So we get this value to be 0, x of 1 to be equal to 1, x of 2 is equal to 2, and x of 3 will become 3. Fair enough. Now putting the values, we get x of k, this is 0, and x of 1 is 1, so we get directly e to the power minus j pi k over 2. For the next term, we get 2 times e to the power minus j k pi plus 3 times e raised to the power minus j 3 pi k over 2. Very well. Now since we have solved for n, which goes from 0 to 3, all we are left with is to solve for k. So solving for k, which goes from 0 to n minus 1, which is equal to 3. First, we solve for x of 0. So, replacing all the k terms by 0. So, this expression, since k is 0, e to the power 0 will give us 1. Similarly, in this expression, e to the power 0 times 2 will give us 2. And consequently this one will give us 3. So we can write it as 1 plus 2 plus 3, which is 6, plus 0j, or in the polar domain we can write 6 angle of 0. Then we come to x of 1, where this expression becomes e to the power minus j pi by 2, since the value of k is 1, plus 2 e to the power minus j pi plus 3 e to the power minus j 3 pi over 2. Now expanding these terms into the Euler's relation, we get cosine of pi by 2 minus j sine of pi by 2 plus 2 cosine of pi minus j sine of pi plus 3 times cosine of 3 pi by 2 minus j sine of 3 pi over 2. Now simply we can plug in the values of the angles and get the trigonometric ratio. So cosine pi by 2 will be equal to 0, sine pi by 2 will be equal to 1. Cosine pi will be negative of 1, sine pi is always 0, cosine thrice pi over 2 is 0, and thrice pi over 2 sine is negative 1. Okay, then now multiplying the coefficients, we get negative j minus 2 plus thrice j, which is equal to minus 2 plus twice j, which can be written in the polar form, where if this is a and this is b, then a squared and b squared, so this becomes 2 squared plus 2 squared angle of tan inverse 2 by negative 2, which is in the second quadrant. So we get 2.8 angle of 135 degrees. Similarly, let us solve for x of 2. X of 2, we get e to the power minus j 2 pi k by 2. The 2 cancels out. All we are left with is pi of k. Pi only, because we have replaced the value of k with 2. Then the next term, e to the power minus j twice pi plus 3 e to the power minus j thrice pi. Now we can expand all this term using the Euler's relation and replacing the angular values. We can get the complex result. I will write it down and not go into further calculation. This will be negative 2, which can be written as 2 angle of 180 degrees. Similarly, for x of 3, we get e to the power minus j thrice pi over 2, 2 e to the power minus j thrice pi plus 3 e to the power minus j 9 pi over 2. So this can be simplified, and the result is 2 minus twice j, which can be written as 2.8 angle of negative 135 degrees. So finally we can get the value x of k to be equal to 6 angle of 0, 2.8 angle of 135, 2 angle of 180 degrees, and 2.8 angle of negative 135 degrees. This is our required discrete Fourier transform. Okay, now let us move on to the magnitude and the phase plots. So for the magnitude plot, let us take the axis So this is the 0th position, the 1, 2, 3. This is 1, 2, and 3, where this is the k-axis and this is x of k, it's magnitude. So at the position 0, we get the magnitude to be 6. At 1, the magnitude is 2.8. At 2, the magnitude is 2. At 3, the magnitude is once again 2.8. This is 2.8, 2, and 2.8. So this is 6, this is 2.8, 2, and 2.8. So this is our required magnitude plot. Now let us go ahead and solve for the phase plot. This is k and this is angle x of k. This is 0, 1, 2, 3, 4. So at 0 the angle is 0, at 1 the angle is 135, at 2 the angle is 180, and at position 3 the angle is negative 135. So this is 135 degree, this is 180 degree, this is negative 135 degree. This is the first position, second position, and the third position. So these are our required magnitude and phase plot. Okay, now let us move on to the next problem. The question is, if the input signal given by x of n is equal to sine pi by 2n, where n goes from 0 to 3, and the system impulse response h of n is equal to (1 to 48), we are to determine the system output y of n. So here both the signals are having length n equals 4. So we can write x of n, which is equal to sine pi by 2 n. So when n equals 0, sine pi by 2 times 0, that is sine 0, is also 0. And again, when n equals 1, sine pi by 2 times 1 is sine pi by 2, which is 1. When n equals 2, sine pi by 2 becomes sine pi, which is equal to 0. And when n equals 3, sine thrice pi by 2 is negative 1. So this is our input signal. And our impulse response given by h of n is equal to 1, 2, 4, 8. So as per definition of a system, as per the definition, if this is a system with an impulse response or a transfer function h of n, we're giving an input of x of n, then the output y of n will be equal to x of n convolved with y of n, h of n. Now, since we are operating in the DFT transform, so this convolution will be circular in nature. So by definition we can write y of n to be equal to x of n, which is circularly convolved with h of n. Now this problem can be solved in two ways. One of which being we can simply circularly convolve these two signals. Otherwise we could use the circular convolution property. Now, as earlier I have shown an example on circular convolution, so I hope you can easily solve this problem using the circular convolution technique. So what I will be concentrating on is the second way to solve the problem, which is using the circular convolution property. So now since we are doing the circular convolution, first of all we must define W of n, which in our case is W of 4, and W evidently is e to the power minus j twice pi over n. And since n is 4, we can write this as e to the power minus j pi by 2, which if expanded using the Euler's relation will give us the result negative of j. Fair enough. So now we can write x of k is equal to summation where n goes from 0 to n minus 1 x of n w n to the power kn, which can be written as summation n goes from 0 to 3. Remember, n in our case was 4, so this will be 3 x of n w4 to the power of kn. Now expanding this summation, we get x of 0, x of 1 wn to the power k times 1, which is k, plus x2 wn to the power k times 2, n being 2, which becomes twice k, and x3 wn to the power of thrice k. Now plugging in the values, x of 0, so x of 0 is 0, x of 1 is 1, again x of 2 is 0, and finally x of 3 is negative 1. So this expression becomes wn to the power k minus wn to the power thrice k. Similarly, we can solve for h of k, which is equal to summation where n goes from 0 to n minus 1 h of n wn to the power of nk. This can be expanded as h of 0 wn to the 0, h of 1 wn to the k, h of 2 wn raised to the twice k, and h of 3 wn raised to the power of thrice k. Very well, once again we plug in the value of h of 0, which is equal to 1, h of 1 is equal to 2, h of 2 which is 4, and h of 3 which is 8. Very well, so we can write h of k to be equal to 1 plus, this is 1 because wn to the power of 0 is equal to 1, so 1 times 1 becomes 1. 2 times wn to the power of k, 4 wn to the power of twice k, wn to the power of thrice k. Now let us solve for wn to the power of 4k, which is equal to e to the power of j twice pi over 4 whole to the power of 4k. So this is equal to e to the power, this 4 and 4 will cancel out, j twice by k, and j twice by k is equal to 1. So wn to the power of nk will always be equal to 1. Understood? Okay. Now we come to the convolution property. Which clearly states that once we are convoluting two signals in the time domain, it will be multiplied in the frequency domain. So simply enough, we can write y of k to be equal to x of k, sorry for the interruption, y of k will become x of k times h of k. So we can multiply wn to the k minus wn to the thrice k, which is the value of x of k, which we got over where? Here. And h of k will become 1 plus 2 times wn to the k plus 4 wn to the twice k plus 8 wn to the thrice k. Now we simply multiply these two expressions. This will be wnk, wn3k, and this is multiplied by 1. When multiplied by 2, this is 2 wnk, and wnk multiplied is 2wn to the power twice k minus 2wn to the power 4k. Then it will become 4wn to the thrice k, 4wn to the fifth k, 8wn raised to the power 4k minus 8wn raised to the power of 6k. Now we can simply write, okay, before that let us solve one more line. Wn to the k, wn to the 3k, 2wn to the twice k minus 2wn to the 4k. We have determined the value of wn to the 4k to be equal to 1, so this becomes 2. 4wn to the power of thrice k minus 4wn to the power of 5k. This can be written as wn to the power of 4k times wn to the power of k. And since wn to the power of, this can be written as wn to the power of 4k wn to the power of k. Since this value is equal to 1, so we can simply write it to be wn to the power of k. So 4 wn to the power of k. This will be 8 wn to the power of 4k, which is 8, minus 8 wn to the power of 6k can be written as wn to the power of 4k times wn to the power of twice k. And since this is 1, we can simply replace it with wn to the power of twice k. Now adding this up, we get, first let us add up the integer values. So 2 and 8, negative 2 and 8, it will be 6, minus 3 wn to the power of k, minus 6 wn to the power of twice k, 3 wn to the power of thrice k. So if nothing is there, we can simply imagine a wn to the power of 0k over here and write it as wn to the power, this one we can write as wn to the power of 1k. There is nothing wrong with that mathematically. So if we compare this expression with this type of expanded expression, so we got wn to the power of 0k, wn to the power of 1k, 2k, 3k, then evidently this coefficient is nothing but the time domain value As such, it is shown as h of 0, h of 1, h of 2, h of 3. So it is fair enough to say this is y of 0, this is y of 1, this is y of 2, and this is y of 3. I suppose there are no objections in that. So if that is the case, we have simply solved our problem. So our y of n becomes 6 minus 3 minus 6, 3. This is our resultant output signal of the system. So the significance of this math is that you can solve it in both ways, whichever way is preferable to you, unless it is mentioned otherwise in the question, where the question paper setter specifies the mode of operation for you. So let us move on to the next problem.